Okay, today we're going to continue with refraction and reflection, but we're going to sort of look at special cases. And the first topic we're going to look at is what we call total internal reflection. So what this happens is only occurs when we go from a high density object to a less density object. So this would be like light going from water to air. So if we look at this first example that shows the red ray, so it shows, you can see the red line comes in. When it hits the air, it's going to speed up. So that means it's going to bend away from the normal, something like this picture does. So that's good. So the second one on the bottom here, the blue ray, it says all we've done is we've increased our angle. So we can see originally the angle there is like about 20 degrees. Now it's about 40 degrees. So if we increase the angle, the same thing occurs, but because that angle's bigger, that means our refraction angle is going to be bigger as well. Okay, so that's still basically just normal. So what happens then if we increase it to the point where the refracted angle is exactly 90 degrees? So if we have a pretty big angle of incidence and then it refracts, and if that angle of refraction is 90 degrees, that means that light's never really going to leave the surface. So it just sort of goes right along the surface of the water. Basically, we wouldn't see anything. So we call that angle the critical angle. And the critical angle is what is the angle of incidence so that the refracted angle is exactly 90 degrees. So when we do calculations like that, all we got to do in our formula, if we have sine theta 1 over sine theta 2, we just put in 90 degrees for our surface number 1 or 2, doesn't matter which one. So then the question then is what happens if the angle is less than the critical angle? So if we get anything smaller, that's like our first two, which are just normal situations. If we get an angle bigger than the critical angle, you can see here, if this angle gets really big, like 50 or 60 degrees, then you can see the refracted angle is below the surface, so it never really leaves the surface, so it just reflects inside, and that's why we call it total internal reflection. So all of the light never leaves the surface, it just reflects inside and stays inside the first surface. So that's the key idea for fiber optic cable. So if we just have a chunk of fiber optic cable, which is just usually just a thin, clear plexiglass type substance, and all we do is we shine a light in, so the light just kind of comes in, and the way it's set up is that plastic is high density, so the light would just reflect back, and it just continues to reflect back and forth as it travels down the length of the wire, or the line. And even if there's bends in it, so let's suppose we had a bend in the wire, it would still just reflect as it goes through. So total internal reflection works really well for anything that's fiber optic. It also is cases where we can create the signal, so in terms of like computer lines and things like that, we can get better quality, they move faster, we don't lose any waste transmission. And the other thing I just want to mention, you guys have all seen this before, when we look at this green ray again, where we're right at the critical angle, what happens in that situation is if you're driving down the highway on a hot day and you look far in the distance, we sort of see a mirage, or we see sort of looks kind of watery, the road. The reason for that is it's sort of the same thing. We actually have hotter air right next to the surface of the road because of the heat of the pavement. And so the heat rays, or the light rays that come off the pavement, actually come up, and then when they hit a cooler air, they actually refract just like they would as if it was water to air or something like that. So if we're driving our car and we're at a long distance away and we're looking at this, basically what's happening is when we see a mirage, we're at the perfect distance where that light ray is at a certain angle, and we end up getting the critical angle. So that's why we don't see the road. It's refracting right at the perfect angle, so we just sort of see that water, shiny sort of looking surface. And that's the same thing when people think they see a mirage in the desert. It's just the same thing. The heat coming off the sand at a certain distance makes it look sort of like water. And our last little topic we're going to look at is how a prism works. And remember, a prism is just basically a clear glass, but it's in a triangular shape. And the reason for that is so we can use it to get white light. And because each wavelength is going to refract slightly different, we can actually split the white light apart. So you can see the white light goes into the prism. It sort of splits inside of it. And then the other angle, because we have two different angles, it causes the white light to refract differently. And it's due to those angles, that's how we get our rainbow, our Roy G. Biv colors. So pretty cool how prisms work. And if we had another prism, let's suppose we put another prism right there and it refracted through, it would come out back as white light again. So two prisms, you can recombine light back into white, so we call it recomposition. If we put white light through a prism and it breaks apart, we call it dispersion, because the light disperses apart into its individual colors. So nothing fancy about a prism, just like I said, just a triangular piece of glass. But water, it doesn't have to be triangular. Round works as well too, but we typically would then get a round sort of rainbow color. And that's how we see rainbows. We have water droplets. Light enters the water droplet and it actually disperses it just like a prism would. And that's how we see our Roy G. Biv rainbow coming out of the water droplet. So if we have millions of them, they're all working together, they're all roughly the same angle, then we get our big massive rainbow when they all do it together. So to have a rainbow, we need mist in the air. We have to have lots of water droplets. We need like a bright light source, so it's got to be a sunny day, and we get our rainbow. And this picture that I have at the bottom is the picture of a rainbow up in the sky. So you can see it's actually round. So the rainbow is totally round. We only see it as a semicircle because the ground kind of cuts off our vision from the rest. So you see we got a full circle, and you can actually see the second rainbow out at the distance there. One kind of key thing is the second rainbow, basically the light splits the original back up again and it reverses it. So you can see we sort of have Roy G. Biv on the first rainbow, but if you look at the other ones, it actually goes the other way. Red is on the inside and violet on the outside, and it would keep going on and on. There's actually going to be a third and a fourth rainbow and so on, but usually the light's not bright enough. We can only see usually just two. And that's it.